Today, we're actually going to cover graphs of polynomials. All right. So just a quick review. Okay. So if you remember, a linear polynomial, which is just 1 degree, is in the form ax plus b. Okay. Now, second degree polynomial is in the form ax squared plus bx plus c. Okay. Same with a third degree polynomial. You have the form ax to the third plus bx squared plus cx plus d, where a, b, c, and d just represent any real number. Okay, so you can just keep on going and going and going, all the way to some finite number n, so some nth degree polynomial will have the form. Here, remember, third degree polynomial means your leading term is to the third power. That's your highest degree. So your nth degree polynomial, bless you, would mean you would have some coefficient next to your nth exponent. So we'll call that an x to the power of n plus, and we'll just call the next one an minus 1 just to keep it in order. Xn minus 1, because if you notice, the degrees always go down, the exponents go down one at a time. N minus 2, x to the n minus 2, and it keeps on going and going and going until you get to your x squared, your x, and then you have some basic constant at the end. Okay, so this is where, let me bring that out a little bit. There we go. Okay, so this is where we know that our an, all of our coefficients, all the way to a0, are all constants. Where the leading coefficient, we just know for a fact that that's not equal to 0. All right. Move that up a little bit. Okay. So now we're going to describe a power function. So a power function is really just a single term that has, as you would expect, just an exponent or a power. That is the product of a real number a coefficient, move that on the next one, and a variable raised to a fixed real number. Okay, so that would be the definition of a power function. All right, so let's give a couple of examples of those. Okay. Oh, well, before we do that, let's give the general form of a power function. Okay. Oh, I can actually put it right next to it. Save space. So the general form of a power function is f of x equals some number k times x raised to the power of some real number p. Okay. Remember, a power function is just one term, where a polynomial can be one or more. All right, so now we'll have our example. So if you have, let's say, f of x equals 3x to the fourth, that's a power function. Okay. Even if you have f of x equals 2 over x to the fifth power, that's actually a power function because you can rewrite it. 2 times x to the negative 5. Okay, so that's a power function. Okay. But if you had, let me move this up a little bit, f of x equals, say, 3 to the power of x, that wouldn't be a power function. Because remember, it's a real number raised, a variable raised to a fixed real number. That's a real number raised to a variable. So you can't switch them around like that. So it's not a power function. Since you have a real number raised to a variable. Okay, which doesn't match our variable raised to a real number. All right. So any questions on that one? All right, leave that up for a few seconds. And I'll just put that here. All right. So now we're going to look at end behavior of polynomial functions. Oops, straighten it up. Okay. So we know any polynomial that has a degree of 2 or higher, we know two things about them. They're continuous, which means there are no breaks anywhere in them, and there are no sharp corners. You have sharp corners when you have like absolute values of a function, but any polynomial function, you don't have any sharp corners. So polynomials of degree 2 or higher do not have sharp corners or breaks in the graph. Okay. Okay, so this means that they are smooth, which means no corners, and continuous. which means no breaks. Okay. So I'll give you examples of what they mean by smooth and continuous. Okay, so let's say, for example, if you have a polynomial graph and it looks like that, that's a polynomial. It's smooth, there are no sharp corners, there are no openings anywhere, no breaks, so it's a polynomial. Even if you have just a straight line, that's a polynomial. Now, if you had a graph that looks like that, or even if you had a graph that looks, let's say, some sharp line pops up there, these are not polynomials. Okay? They're functions, they're just not polynomials. Okay? Or let's say if you had a function that looks like this, but it stops there, then it picks up here. This is not a function. Let me kind of separate that a little bit. I mean, not a polynomial. Simply because, you know, it has breaks. Or a break. So it's not continuous. All right. So any questions on any of those? All right. I'll leave those up for a few more seconds. Oh, actually, just a quick, we're going to, a little extra. Okay. Just a quick review if it's been a while since you've actually worked with degrees. A degree of a function is the sum of the, you can say the exponents of each term. Okay. Now, if you have a polynomial with multiple terms, the highest degree will be the degree of that whole polynomial. The highest degree term is the degree of the polynomial. Okay. We'll give you a couple of examples. So if it's been a while, hopefully this will refresh your memory a bit. So let's say, for example, if you have f of x equals, let's say, 3x squared plus 2xy plus 3xy to the third plus 7. Okay. Each individual term has their own degree. Okay. So this one, your variable is squared. So this one has degree 2. X and y, if you think about it, that's x to the first and y to the first. So this one's degree 2, if you add those together. This one, you have x to the first and y to the third. So this term is degree 4. And this one's actually degree 0 because if you multiply by x to the power of 0, you still have just 7. So this is degree 0. Okay. This one's the highest. So this entire polynomial is degree 4. (3x squared plus 2xy plus 3x y to the third plus 7) has a highest degree of 4. So the entire polynomial is degree 4. All right. So any questions on that one? All right. So all you have to do is just each individual term separated by the plus or minus signs. Just count the exponents. That's your degree for that term. Whatever the highest one is, that's the degree for the whole thing. All right, leave that up for a few more seconds. All right. Okay, so we're just going to remember a couple of key graphs. Okay, so let's say if you have that's your x, that's your y-axis, and this is your x squared. Okay, so we know it goes up and to the right and up and to the left. Uh-oh, straighten that up a little bit. Now we know that if we put a negative coefficient in front of it, it flips it over the x-axis. So if we get negative x squared, it just flips it. All right, so let's just flip it like that. So that's your f of x equals negative x squared. Okay. Since we're talking about endpoints, you want to notice that the endpoints go down and to the right and down and to the left. Okay. So what if we have, let's say, look at our graph. We have our x, we have our y, and we'll draw one right next to it since we're going to be comparing them. Move that up a little bit. Yeah, that's good enough. X, and that's our y. Okay, so if we just have our straight line straight right through there, that's just f of x equals x. Now remember, if you multiply by negative, it just flips over the x-axis. So if that just flips, uh-oh, missed. Now turn it this way a little bit. There we go. All right, so if you get that same graph, you flip it, then that's f of x equals negative x. All right, and one more. Well, two more technically. You have x, you have your y, and since we're going to be flipping that one, might as well draw another one. You have your x, you have your y. Okay, so we know that if we wanted to graph f of x equals x to the third, it kind of looks like that. So if we decide to graph f of x equals negative x to the third, you just get that entire graph and you flip it. Move that up some. So now our graph will look like that. Okay. Now these are important because we're going to focus on the endpoints. Okay. So if you notice on this one, as x gets bigger, as it goes further and further to the right, your f of x or your y gets bigger. So as x keeps on going towards infinity, your f of x or your y is just going to keep going towards infinity. So we know that your f of x approaches infinity, or it keeps getting bigger, as your x gets bigger. So as it goes to the right, it's going to keep going higher. On this side, as you go to the left towards negative infinity, you notice it still continues to get higher. So your y value, f of x, actually keeps getting bigger, so it gets closer and closer to infinity, but this time your x is going in the opposite direction. So it's going to be as x approaches negative infinity. All right. Any questions on that one? Okay. Now if you notice on this one, as you're going towards the right, or as x is getting bigger and bigger and bigger, your y is going towards negative infinity. So you see your f of x, not equals, approaches or gets closer and closer to negative infinity as x gets bigger. Okay. You can see also as you're going towards the left, or as x is getting smaller and smaller, negative, 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 just deeper negative numbers, it's still going towards negative infinity. So we see f of x approaches negative infinity, even if x is getting smaller and smaller. So as the x approaches negative infinity.